Before we even begin the study of calculus, I want to take a look at an important application that we will come back to a few more times in the course. Have you ever wondered how your calculator knows the value of a square root, or of a logarithm, or of a trigonometric function? In this lesson, I'm going to try to motivate the need to find the slope of a function by considering this question that we have over here. How would you estimate the square root of 11 or the square root of 5 over 4 without a calculator? What I'll show you in this lesson is the basics of the trick that your calculator uses to approximate the result. It relies on the point-slope equation of a line, which you should already be familiar with. If you're given one point, x1, y1, and the slope m of a line, all other points on the line can be found with this expression that we have here. Y minus y1 is equal to m into x minus x1. So you should already be familiar with this, and this is about as difficult as this class is going to get. By examining the question that we have at the top of the page, what I hope you get out of this lesson is an understanding of why we may want to find the slope function, but I do want to emphasize that this is not going to be the only reason that we may want to find the slope function of a function. I'm also going to show you how to program functions into your calculators, which you may or may not already know, and you're going to have your first derivative shortcut. However, we will not put a box around it yet because we still need to do a little bit more work on it before we're ready to do so. So let's begin by focusing on the square root of 11 for a sec. Now, most students would probably recognize that the square root of 11 is between the square root of 9 and the square root of 16. And the square root of 9 and the square root of 16 are known values. The square root of 9 is 3, the square root of 16 is 4. But we know also that the square root of 11 is much closer to the square root of 9 than it is to the square root of 16. So most students would take this approach of taking numbers slightly bigger than 3 and squaring it until we get close to 11. So for example, they may look at 3.1 squared, 3.2 squared, 3.3 squared, and 3.4 squared, and use these values to try and approximate the square root of 11. Very quickly, 3.1 squared is 9.61, not such a great approximation. 3.2 squared is 10.24, which is better but not great still. 3.3 squared is 10.89, and 3.4 squared is 11.58. So we don't have a great approximation for the square root of 11, but we do know that it exists between these two values, and we can write down that the square root of 11 is somewhere between 3.3 and 3.4. And in a lot of cases, this is going to be good enough. However, we can actually do better by approximating the curve y is equal to square root of x with a line. By inspection of the graph of the square root of x, which we have over here, we can see just how close the points 9, 3 over here and 11 square root of 11 are to one another. If we introduce the tangent line to the point 9, 3, which I've done over here, this red line is tangent to the curve y is equal to the square root of x at the point 9, 3. We can see that this red line is a very good approximation to the blue curve in the vicinity of x is equal to 9. The reason that we've done this is because thinking about curves is hard, but thinking about lines is easy. We can use the point-slope form to construct the equation of this red tangent line to the curve at 9, 3. Let's do so together. Y minus y1 is equal to m into x minus x1. Substituting our known values, we have y minus 3 is equal to m into x minus 9. And at this point, we're a little bit stuck because we don't actually know the value of m. If you're willing to trust me though, I'll give it to you. M at this point 9, 3 is equal to 1 over 6. And this allows us to continue. So we have here y minus 3 is equal to 1 over 6 into x minus 9. And a little bit of simplification later, we get y is equal to x on 6 plus 3 on 2. Now, it's not really necessary for us to program this into a calculator, but we're going to be using function assignment quite a lot during this course. So let's go ahead and do so. On our calculator, to do the function assignment, we would have to type f followed by brackets, followed by x, and move forward so we get out of the brackets. Then to get to our assignment operator, we want to press this blue control button followed by this button here next to the 9, which I call my template button. So control that, and there we go. This might sound like a lot to remember, but you're going to be doing it so often that you're going to be a pro in no time. Finally, we're going to type x on 6 plus 3 on 2 and press enter to do the assignment. Finally, we can use this to evaluate f of 11. And we get over here 10 on 3. If I go back to my whiteboard, what this means is that the square root of 11, which is approximately equal to the y we just calculated, well, that's equal to 11 on 6 plus 3 on 2, which is 10 over 3. That's in harmony with, but much nicer looking, than the result of the guess and check method that we were using before. It's also very, very accurate. On the calculator, if we were to compute the square root of 11 and hit Control Enter, we get 3.31. 10 over 3, on the other hand, is 3.33. That's a minuscule difference, so I think you'll agree that our method is pretty good. The problem is that while this method was excellent for approximating the square root of 11, you can see that it's going to be really terrible for approximating the square root of 5 over 4. You can see here that point 5 over 4 is pretty far away from the red tangent line to the curve at 9, 3. We could repeat the procedure though by drawing another tangent line to the curve at a convenient point, say 1, 1, which is what I have over here. And now we can use this tangent line to approximate the square root of 5 over 4. Now, as you can see from what I've sketched here, the slope of this tangent line, the slope of this tangent line is different from the slope of the red tangent line. In fact, the slope of every tangent line to y is equal to square root of x is going to be different from each other. So, here's a question, finally. How did I know that the slope of this red tangent line was 1 over 6? The answer is, it's because I know the actual slope function of y is equal to square root of x. The slope function of y is equal to the square root of x is another function. It takes any x value, such as x is equal to 9, or x is equal to 1, and what it's going to do, it's going to spit out the slope of the tangent line to the square root of x at that x value. Finding the slope function forms the first half of the study of calculus. In this course, we will look at techniques for finding the slope function, called the derivative, and we will study concepts associated with it. Okay, so let me now show you what the slope function is. If f of x is equal to the square root of x, then the slope function f prime of x is equal to 1 over 2 square root of x. This pattern that you see over here comes up so often that it's almost worth remembering as a shortcut, but we won't box the formula yet because there's a bit more to it than what we see here. And it would be useful to first learn how we obtain this second line from the previous line. Here's how we use the slope function now. F prime of 9, which is what we evaluated over here, well, that's got to be equal to 1 over 2 square root of 9, which is equal to 1 over 6 as advertised. That's how we were able to get the slope of the red tangent line. If I want to focus on this black tangent line that I've just drawn at the point 1, 1, I use my slope function again. F prime of 1 is equal to 1 over 2 square root of 1, which is equal to 1 over 2. This allows me to use my point slope equation again. Y minus y1 is equal to m into x minus x1, where x1, y1 is the point 1, 1, and m is 1 over 2. Plugging in our values, we're going to get y is equal to 1 over 2x plus 1 over 2. Okay, just for good luck, let's practice assigning this to our calculators one more time. This time I want to program it in as g of x. So g parentheses x, and then I move out of that, control template button, and my function is 1 over 2x plus 1 over 2. Now I'm ready to evaluate g of 5 on 4. Once again, we get a nice looking expression. Let's do that in decimal form, 1.125, and compare that to the actual square root of 5 on 4, which is 1.118. Once again, the value that we obtain, 1.125, is pretty close to the actual square root of 5 over 4. So in this video, you got some intuition for why we may want to find the slope function, and you saw a practical application of why that's quite important. In subsequent videos, we will begin building up our techniques for calculating these slope functions.